Welcome back to the course entitled Symmetry, Stereochemistry and Applications. Previous class we have discussed about the topicity of different carbon centers. So, we will continue our discussion in this direction today. So, in today's class we will discuss about topicity of ligands and faces. So, in a molecule there are different atoms or group of atoms that are connected to different carbon centers, and then when we have similar group of atoms in a molecule, what we see is that by replacing of those groups by a different group can result in different types of molecules. So, we can say that homomorphic atoms or groups can be classified as homotopic, enantiotopic, and diastereotopic. So, homomorphic atoms means the atoms which are same or groups which are same. So, now we will try to define these three different types of topicities of the ligands or the groups that are associated with a carbon center. So, let us start the discussion with homotopic groups. Homotopic atoms or groups. Homotopic ligands in a molecule are those whose position can be interchanged by rotation about a proper axis of symmetry. That is C n with n greater than 1. In Greek, homos means same and topes means place. So, let us try to understand the topicity of different hydrogen atoms that are connected to this carbon atom, which is the first carbon atom of acetic acid. These hydrogen atoms, which are marked here as 1, 2 and 3, these three hydrogen atoms H1, H2 and H3 H3 are homotopic because they are related by C3 symmetry. So, by rotation about this axis 120-degree rotation, H1, H2 and H3 can interchange their places without doing any change in the molecule. Therefore, these 3 hydrogen atoms can be termed as homotopic hydrogen atoms. Let us try to take another example. An example of a cyclic compound, cyclopropane, in which I have 2 chlorine atoms in the trans position. So, the hydrogen atoms marked A and B are homotopic. Why? Because this H A and H B can interchange their places if I rotate the molecule through this C2 axis, then this hydrogen will go there and this chlorine will come there and the molecule will remain unchanged. Now, there is another way to test whether they are homotopic or not. So, what we are trying to do is now we are trying to replace Ha by bromine. So, what we get is this molecule. And on the other hand, if we replace Hb by bromine, what we get is this molecule. Suppose these are compound number 1 and 2 originating from the parent compound. So, what is the relationship between these 2 compounds 1 and 2? If you look at it carefully, they are superimposable mirror images. Therefore, 1 and 2 are same compound. Right? If we look at the other 2 hydrogens, Hx and Hy, the same relationship is valid. Hx and Hy are also homotopic groups. Now, let us try to understand what happens when we call a group as enantiotopic. A pair of ligands in a molecule is said to be enantiotopic if they are interchangeable by Sn axis. And as we know, S1 is equivalent to sigma plane and S2 is equivalent to I. That means, the molecules or the groups in a molecule related by a sigma or I are called enantiotopic groups. What happens when you substitute those enantiotopic groups by another atom, one after another, one by one? You can generate two molecules which are essentially enantiomers, and from the product that it generates as enantiomers, we call that those two atoms or pair of atoms as enantiotopic atoms. So, let us try to see this with one example. Suppose we have a chiral center with two different groups A and B, and carbon center with two groups A and B and two atoms which are identical X. These two groups are related by a sigma plane, that is the plane of the projection, this plane of projection is your sigma plane. And if we replace, suppose if I tell this as x1 and that x as x2, if we replace x1 by y, we would get this molecule. And if we replace on the other hand x2 by y, we would get this molecule. This molecule 1 here and this molecule 2, they are pair of enantiomers. Therefore, these atoms x1 and x2 are enantiotopic atoms. Hope I am able to make you understand what does enantiotopic groups or enantiotopic atoms mean. What you can see here is that this particular carbon has become a chiral center after replacement of one of the two enantiotopic groups. So, this chiral center, this carbon center is called a pro-chiral carbon or pro-chiral center. Let us see this with another example. Suppose if we take this molecule, what is this molecule? This is a meso compound. So, we write it as meso 2,3 dichlorobutane. So, this compound has two hydrogens, namely HA and HB. If we rotate about this bond by 180 degree, what we would get? We would get this arrangement. Just by rotating about C2, C3. So, what do we see in this molecule? This molecule has an inversion center I, and these hydrogens HA and HB are related by the inversion center I. Therefore, HA and HB are enantiotopic. Let us try to see what happens if we replace HA or HB one after another by bromine. So, at first, if we replace HA by bromine and leave HB as it is, we get this molecule. And if we replace HB by chlorine, bromine, and keep the hydrogen intact, what we get are a pair of enantiomers. How do we see that these are pair of enantiomers? We take this molecule and rotate the entire molecule in plane by 180 degree, and we get this orientation. When you rotate this molecule by 180 degree, these two chlorines will come to the left hand side, this bromine will come here, and the hydrogen will come here, and the CH3 groups will remain as it is. So, now can we see that this group molecule 1 and this molecule 2 are mirror image of each other, and they are non-superimposable mirror image. So, 1 and 2 are non-superimposable mirror images, therefore, they are enantiomers. Therefore, these two hydrogens can be termed as enantiotopic hydrogens. Let us take one more example. Cis 1,2 dichloro cyclopropane. So, in this case, let us first draw the molecule. This HA and HB are related by a sigma plane, that is the plane which bisects the molecule in this perpendicular direction. Therefore, H A and H B are so now if we try to simply replace H A and H B by a different group, if we try to replace this H A or H B by a bromine, we would generate two compounds which I am drawing now. These two compounds are again a pair of enantiomers. Therefore, these two compounds can be termed, these two hydrogens can be termed as enantiotopic hydrogens. Now, let us move to diastereotopic groups. From the name itself, you can now understand that by replacement of two atoms by different group, it should generate a pair of diastereomers. So, the definition is two atoms or groups are said to be diastereotopic if replacement of those atoms or groups by homotopic ligands generates a pair of diastereomers. Diastereomeric groups cannot be interchanged by any symmetry operation, that is Cn, Sn, sigma or I. Let us try to see this with one example. Let us take the example of this chloroethene. Here we have two hydrogens, H A and H B. If we replace H A by chloro, we get this compound, and if we replace H B by Cl, we get this compound. So, this is the Z isomer and this is the E isomer of the 1,2-dichloroethene, and these two compounds that we have formed we know are diastereomers, because they are not mirror image relations. So, these two hydrogens H A and H B are diastereotopic, and you see that there is no symmetry operation that can interchange H A with H B. So, let us try to see this with one more example of cyclopropane, which has two substitutions chloro and fluoro in the transposition. So, this H A and H B that I have marked, let us see what happens when you replace H A and H B separately by F. So, what we see here is that point number 1, this H A and H B cannot be interchanged by any symmetry operation C2, Cn or sigma or I, and then when we replace H A by F, we get this molecule. When we replace H B by F, we get this molecule. What we see here is that this F and F are trans, here the two F's are cis. Therefore, these two compounds are again, they are not mirror images. They are, therefore, they are diastereomers, a pair of diastereomers. So, those two hydrogens H A and H B, they are diastereotopic. Let us see with one more example how these diastereotopic hydrogens can be easily identified. See, in the previous example also, this particular center was not chiral center, it was a prochiral center. But after replacement of fluorine, that carb center has become a chiral center, because now you have 4 different groups attached to that. Similarly, here you see that this particular carbon is prochiral, and these two hydrogen atoms H A and H B are not related by any symmetry. So, now if we replace H A by OH, I am sorry, here I think it should be OH. And if we replace on the other side H B by OH, what we get is this molecule. What we notice here is that in this molecule you have both the OH groups on one side, here the two OH groups are on the opposite side. So, these two compounds are diastereomers. So, this HA and HB are diastereotopic. So, we conclude this lecture today with a note that today we have discussed about homotopic, enantiotopic and diastereotopic ligands. So, in the next lecture we will discuss about the homotopic, diastereotopic and enantiotopic phases of molecules.